Welcome to the 1.13 notes. Today we're talking about removing discontinuities. And the big idea behind removing discontinuities is we have a function, normally a piecewise function, with a missing value. And we want to figure out, well, how could we pick a value? How can we pick a value that would make our function continuous? And so that is the big idea. We have a function that has a missing value. So if you look through some of these problems, we don't know what k is. If you scroll down, we don't know what a is. We don't know what k is again. So we have something we don't know. We want to figure out what is the number that would make this function continuous. And so a reminder, there are 3 conditions for continuity. One of them is that the point has to exist. The second one is the limit has to exist. And the third one is the point has to equal the limit. And so let's see how this applies to this one and how we can use those 3 conditions to help us figure out what is this missing value. So example 1 says, it is known that the limit as x approaches 4 exists and f of x is continuous on the interval negative infinity to infinity. Find the value of k. So this is the most important thing, is that f of x is continuous. It's continuous on all real numbers, and so that means that there's no point inside this function that's like a hole or a jump or anything. And specifically, something we know is that the limit as x approaches 4 exists. And so we are concerned about this function, and the place that we are nervous that it might be discontinuous is at 4, because that's where this function breaks into 2. This function right here, based on what I see, is going to be quadratic, and quadratics don't break anywhere. And this function right here is linear. That doesn't break anywhere. But 4, that point is the place where it possibly could break. And so we need to make sure it's continuous at 4. So if it were to be continuous at 4, these 3 things would have to be true. F of 4 would need to exist. The limit as x approaches 4 of f of x needs to exist, which we know it actually does exist because this problem tells us it does. But one implication of it having to exist that will help us here with piecewise is that if a limit exists, the left-hand limit exists, or the left-hand limit equals the right-hand limit. So keep that in mind. So those are the same. And then the last condition is that f of 4 equals the limit as x approaches 4 of f of x. So those 3 things have to be true. And so how does that help us? Well, we need to figure out what the value of k is. So let's start. F of 4 exists. Okay, so that means that if I were to plug in 4 into this function, that would help us find k. In this condition, if I were to plug in 4 into this function, I would plug it in for this part right here. And because that's where x is greater than or equal to is the important part. And so I could do that and I could figure out what f of 4 is. But I already know that exists because this is continuous, and that doesn't help me find k. So let's see if the other thing helps us. Number 2, the limit exists. So that means that if the limit exists, because it's continuous, we know that's true. If the limit exists, that means the left-hand limit's got to equal the right-hand. So that means that the limit as x approaches 4 from the left equals the limit as x approaches 4 from the right. And so if that were to be true, that means when we plug in 4 into the function, this is the function that defines f of x from the left of 4. This is the function that defines it from the right. So that means if we were to plug in 4 there, those 2 things would have to be the same. So if I plug in 4 here, even though I don't know k, I would do 4 squared minus k. And then for this one, I plug in 4, and I would get negative 3 times 4 plus 18. 4 squared minus k is 16. Negative 3 times 4 is 12, negative 12. Negative 12 plus 18. So we know that this has to be true because this function is continuous. And so now we can just solve for k like we would solve any linear equation. So I'm just going to clean this up. Negative 12 plus 18 is 6. Subtract 16 on both sides. I get negative k equals negative 10, and then therefore k equals 10. So based on what we get, k is the missing value. The missing value is 10. That would make this true. So what we're basically getting is f of x equals x squared minus 10 negative 3x. You don't have to write this. Well, you can write this down, but like you don't need this as part of your answer. But this function right here is a continuous function. And so let me show you real quick what the graph of this looks like. And then I'm going to have you guys sketch it in your blank. So I'm going to go to Desmos real quick. And then I'm going to type in x squared minus 10. And then the way that you do a domain is you put brackets. And then this is for when x is less than 4. And then negative 3x plus 18 when x is greater than or equal to 4. And so if you look right here, these 2 points are the same. They touch and the limit exists. And so we did correct. We found the right value. But maybe we had figured out, maybe the value was 1 instead of 10. See how that's not correct? See how there's a huge discontinuity there? And so we have to find the value that makes that true. And negative 1 would, or minus 1, or 1 would not be the right value for k, but 10 is. And so if you want to sketch this graph right here, it should look something, I mean, you just looked at it, but roughly this is what this graph would look like. So it is a piecewise function, but they meet at 4, 6. They have the same limit, etc. So that is it. We figured out what k would be to make this continuous. So these next couple problems are just going to be us practicing that. A lot of them are going to be pretty straightforward. Some of them are going to look slightly different, so just be prepared for that. But let's go on to example 2. So this says, what value of a makes the function continuous at x equals 1? So if it were to be continuous, then f of 1 has to exist. Remember, the limit as x approaches 1 has to exist. And then our last condition is f of 1 has to equal the limit as x approaches 1 of f of x. Normally, the second condition is going to be the one that helps us the most. So because that has to exist at 1, the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. And so let's go ahead and try to figure that out. So the limit as x approaches 1 from the left, I use this function, and I'll get negative 3 times 1 minus 3. And then the limit as x approaches 1 from the right of f of x, I would do 2. I don't know what a is, so I just leave that blank. And then I plug in 1 plus 1. I'm going to get negative 6 equals 2a plus 1. I'll subtract 1 on both sides. I'll get negative 7 equals 2a. And then I'll get negative 7 halves equals a. And that's our answer. If you wanted to check your work, you would just put it in Desmos, and you would see that they connect. And this is a sketch. I did this earlier. But if you were to graph that function with negative 7 halves plugged in for a, it would look like this. And here at this point that we're nervous about 1, it is connected. There's no hole, it's connected. Okay, going on to the next one. So this one is a little different, but this is example 3, and it says f is continuous for all real numbers. What is the value of k? So this one is a piecewise function, except it's slightly different because it's a piecewise function where most of the graph looks like one thing. So it's going to look something like, this is not what it actually is, but basically the graph is going to change at negative 2, but for most of the function except for 0, you're using this function to define it, but then there's this value k somewhere. So this is the point negative 2k, and we don't know what k is. So this is different than like half the graph looking like this and half the graph looking at this one. This is indicating that there's a removable discontinuity. And so let's go through some of our conditions and see if they can help us. Because this problem is different than the last one, we're going to operate a little bit different. So the first thing we would know is that f of negative 2 exists. And in this case, this is where it says x equals negative 2, so I would use this function to figure out what f of negative 2 is, and right now all we know is that that is k, but we don't know what k is. The other thing we know is that the limit as x approaches negative 2 exists, so that's something that we know. Okay, and then we're going to get back to that part. It equals exists. I guess it can't really equal exists. But then we also know that f of negative 2 has to also equal the limit as x approaches negative 2 of f of x. So let's start by seeing if we can figure out what is the limit. And we can just go ahead and use this function because it's only not defined for negative 2, but that means that all of the values a little bit smaller than negative 2 are defined in using that function, and all the values a little bit bigger than negative 2 are defined in using that function. So let's start with that and see if that helps us out a little bit. So the limit as x approaches negative 2 of f of x equals, well, I'll go ahead and put that function in. We have x squared minus 4 all over x plus 2. And looking at this, you might realize that if we plug in negative 2 here, we would get 0 over 0, which makes sense because we had another value for negative 2 anyways. And so I have to use my indeterminate form strategies. I see that this is a quadratic, and so I can factor the top because it's a difference of perfect squares, and I would get x minus 2 all over x plus 2 all over x plus 2. And then these would cancel out. I'll get limit as x approaches negative 2 of x minus 2. And then I'll get negative 2 minus 2, and that equals negative 4. So I figured out that the limit is negative 4. But that doesn't help me figure out, well, it will help me, but I don't know what k is yet. However, I do know that f of negative 2, based on our third condition, has to equal the limit at negative 2. And so the limit at negative 2 is 4. And then f of negative 2, we talked about this earlier, but f of negative 2 is k. So I'll get k equals negative 4. And that is my answer. And so basically, that means that this hole that we see up here, that hole, instead of it being there, it's actually just going to come in here, and it's going to fill in this point right here, and it's going to make that a continuous function. Even though it's a piecewise, it's still continuous because there's not actually a hole in there anymore because k just equals negative 4. Okay, a couple more. How many more do we have? 2 more. So what value of a makes the function continuous at negative 3? So this is, again, kind of similar to the last one. The whole function is basically defined by this here, this quadratic, except for at x equals 3, there's a hole that k replaces. So most of the function is defined by this quadratic. I don't know exactly what this quadratic looks like, but basically it's going to be something like this. And then there's going to be some kind of hole there in this k. We're trying to figure out what does this y value have to be? What does k have to be so that it can fill that in so that there's no longer a discontinuity? And so this one's going to be more similar to the last one we did. But we know that f of negative 3 is k. Okay, so that's the part we know. F of positive 3. Also, one of these should say, sorry, there is a mistake here. Let's make this one say positive 3 instead of negative 3. I'm gonna take this and move it over here instead. Those should be the same number. Sorry about that. Oh, it says negative 3 up there. Okay, actually, never mind. Sorry, we're gonna change this to negative 3. Sorry for the confusion. And I'm gonna pick this back up and put it back over here. Okay. Pretend that looks great. Okay, so we're trying to figure out negative 3. So f of negative 3 equals k. Because that's what you would use to find k. And then we'll start by finding the limit. Let's try to find the limit as x approaches negative 3 of f of x. So the nice thing about this one is if I plug in, sorry, I'm using this function right here because this is the function that is a little bit less than negative 3 and a little bit greater. If I plug in negative 3 into this one, it just works out nicely. It's going to give us a finite number. So I'll get 2 times 9 minus 15 minus 3. That gives me 18 minus 15 minus 3, which will give me 0, I believe. And then, based on that, so those two things have to be true. It has to exist. The function value also has to exist because we're trying to make it continuous. And then the last condition of continuity is that the limit as x approaches negative 3 of f of x also has to equal the value at negative 3. Well, the limit is 0, and the value we know is k, so that means that k equals 0. And so that means that this function actually probably looks more like this, and then we come in, and this part right here, the k, fills in that hole, making it continuous. Okay, last one. Feel free to try this on your own. This one's a little bit more like the original ones because all of the values less than 1 are defined by the function negative x plus 1, and then all the x values greater than or equal to 1 are defined by 1/2 x minus 2. And so, yes, we know that f of 1 is going to exist, but that is not going to help us find the k value. What will help us find the k value is the fact that the left-hand limit always has to equal the right-hand limit for the limit to exist. And because it's continuous, we know the limit exists, so that means that this fact right here must be true. So if I plug in the limit as x approaches 1 of f of x, I'll get negative x plus k. Oh, sorry, I should be plugging in 1 there. So I'll get negative 1 plus k equals 1/2 1 minus 2. Negative 1 plus k equals 1/2 minus 2. Negative 1 plus k equals negative 1/2. Add 1 on both sides, and I'll get k equals negative 1/2. And that is our answer, and that is the value that would make this function continuous. That would be where the two functions, that would help the two functions meet at the same point. So if you have any questions, send me an email. Best of luck.